Now let's do another example. Here we have a refrigeration cycle. What is given is Q dot C is 8,000 kilojoule per hour. Tc is -5 Celsius. W dot cycle is 3,200 kilojoule per hour. And Th is 22 Celsius. That means you want to keep your refrigerator at -5 Celsius while the ambient temperature is at 22 Celsius. And in order for you to do that, you have to consume electricity and you have to consume 3,200 kilojoule per hour. And then the amount of heat you have to remove from the inside of the refrigerator is 8,000 kilojoule per hour. We're looking for two things: actual coefficient of performance beta and beta max. We can find beta from the definition. Beta is coefficient of performance, and the definition is purpose over cost. The purpose of a refrigeration cycle is to keep it cool, and a direct reason to keep it cool is QC, and the cost is electricity you pay, which is W cycle. However, what we have is QC dot and a W cycle dot. So what we can do is to divide both the numerator and the denominator by time. And divided by time, the syntax becomes QC dot and W cycle dot. So now we can plug in the numbers. QC dot is 8,000 kilojoule per hour, and then W dot cycle is 3,200 kilojoule per hour. And pay attention here, both units are not SI unit. But there's no need for us to convert them to SI. Why? Because they will cancel anyway. Okay, so our solution for beta is 2.5. That's part 1. And part 2 looks for the maximum coefficient of performance, beta max. The equation we derived was Tc over Th minus Tc. We plug in the temperatures. Like we said before, when you plug in temperatures, always make sure you use Kelvin. Tc is -5 Celsius plus 273 to convert it to Kelvin, and then do the same thing. Solution for beta max is 9.9. So do you think this design is possible or not? Beta is 2.5 and the beta max is 9.9. So beta is actually smaller than beta max. That means your design doesn't violate second law of thermodynamics.